So, did you have a chance to do lesson 19 on the lesson on persistence last week? Okay, when I was out of town, all right, I couldn't post a whole lot, but I posted the materials there for the lesson. And also, I mentioned that you could use there the family school that has basically the lesson here on persistence, and it has a pretty good summary or biography on the life of John Harrison. Okay, did you have a chance to do that? So this is the image that we have there of John Harrison. Okay, so Nicola says I'm working on it.
Yeah, I had many.
Go ahead.
I said I had many chances.
Many chances. Did you take any of those chances?
Probably no, I did not take any of those chances.
So yeah, the chances are interesting. Taking your chances is one way. So I thought so, but actually the interesting thing was that I was just fascinated by the life here of John Harrison and the work that he did. Okay, and really the persistence of the things that it took for him, the time that he took really in his life to come up with a chronometer. Okay, so the idea was that the everyone was trying to find ways of measuring longitude better. Okay, and so the British Parliament passed a law basically establishing a price, a very sizable price. I think like it was like £20,000. That would be equivalent to about £2 million of sterling pounds nowadays. So that would it's a fortune really, and it was a prize to whoever could make a practicable and useful way of measuring longitude at sea. And so John Harrison was, of course, interested not only on that, but the problem of measuring time. He was a clockmaker. And so he worked on that for many, many years. Okay. So in fact, here in this kind of biography, we have, about, it shows that, for example, to do the first clock, the H1, okay, it took him 5 years. Okay, have you spent that long into something? All right, we are going to see an example here of H1. H2, the second clock that he made with some modifications, it took him 3 years to make that one. The third one, he spent 17 years working on that watch, on that clock. Okay. And then finally, the H4 was the chronometer. And he actually, the third one, he never tried it at sea. So during this time, he basically was able to come up with the fourth watch. Okay, oh, there's a broken link to that. But it's a chronometer. So here we have the midsection of H1. Okay, all right. This is a picture of how H1 look, and this is H4. This is the chronometer that he came up with, and it was very, very accurate. So a beautiful, beautiful, frankly, a love story. Okay, if you want to be a love story, because it shows the persistence and the love of this man dedicating his life to build something that would save thousands of lives. Okay, it was very common really for sailors to get lost at sea or to estimate wrong their latitude. They are not the latitude. The latitude was easy, but the longitude, and then hit an island or a rock, or completely miss where they were. And so with the efforts really of John Harrison in making this watch were just amazing. So have you done the experiments on measuring your latitude and longitude? Have you done that again? Okay. You remember that that was one of the things that we were going to do as an assignment. Okay. What has happened? What have you experienced? Have you experimented with that? I'm going to take the silence as kind of saying, not too much. Okay, so
I haven't done the thing.
Eh?
I haven't done it yet.
Okay, so let me share with you my.
No good.
Go ahead.
I said I'm just no good at experiments. I just never fall through with them.
Well, it is not easy. Okay, all right. So the question was, have you tried your experiments on measuring latitude and longitude? Okay, that was the question, Sabrina. So, Rodney, I understand, and I tell you, it's not easy, okay? And but it's something, to actually try, all right? So, remember when I share my experiment, my experience before with you, okay, in measuring longitude, we had the lesson there. I came up with an error of 110 miles. So that was my estimate, and this is my home, all right? So it wasn't very nice, okay? Annika says, we have had only a few sunny days, and I hate to admit, but I haven't even looked at the times on the right day yet. Sorry, I will make it a point to do it on a sunny day and SSAP. Yeah, excellent. I tell you, it's difficult because you need a sunny day, okay? And you need to be there at noon, and you need to dedicate the time, but it is really worth doing the experiment. So the week before I went to Disneyland, okay, and actually I have to tell you, I was tempted to try this there in California because I was at a different location, so I would like to. And I had a couple of sunny days, but I thought that it would have been weird to spend my vacation time doing this instead of being with the family. But anyways, I was tempted. But I give it the week before I went on vacation, there was a sunny day here in Utah, and so I took advantage of that, and I did a second try to the experiment, okay? And so on January 22nd, I did my second try of that, all right? Utah haven't had a lot of sunny days, and so, but that week, January 22nd, I remember it was really, really bright and nice. Okay, so I did that. I went out to my patio, and I put the level on the ground to actually find a level place. And what I noticed was that when I did my first try, okay, on the experiment, okay, when I was measuring things here, all right, actually I put the level here on this piece of ground, and I noticed that I was off a few degrees, all right, and so probably that may have affected my measurement of things, okay. And so now I found a place that was level, okay, and I did another contraption. This was a smaller one, a shorter one, so I could have a more manageable shadow, okay. So, and I started quite early here, and I'm going to show you here the movie. This is a movie of what happened, okay. So let's watch this.
All right, So this is my third attempt at measuring longitude, and this is the contraption that I've made.
It was actually the third, yeah.
So I made this a little smaller in order to have a shorter shadow, and I started earlier measuring the shadow, the length. Okay, so if we focus here, and I started at 520 UTC, and then I measure the length of each one of the radius there. And when I got closer to the shorter time, I started measuring every 5 minutes, and then every minute there. It's pretty hard to do the measurement, but you can clearly kind of see that the shortest shadow there is at probably I'm going to call it 528. Oh, 728, sorry, 728. So then we will do the calculations on that. I was measuring basically the length of the shadow using a ruler, putting the ruler at the base. Actually, I also measure this just perpendicular of where it would go with this plumb line in order to get the base there of my shadow. All right. And so that's it. So let's see how this calculation turns out now with another set of metrics. Okay.
All right. So do you see what I did? What was the experiment? The issue here was trying to measure the length of the shadows and seeing at what time the shadow would be the shortest. Okay, because the shortest shadow basically indicates there the noon time here in the place where I was. Okay, and then I would put the time, the UTC time, for the length of each one of the lengths of the shadows. So as I was noticing the shadow getting shorter and shorter, then I started measuring in smaller intervals, okay? And then I noticed that the shadow was starting to get larger. And so, it kind of, if you join all these, it would be like a hyperbola, all right? That is kind of how it goes, all right? Yes, it is kind of like a sundial, all right? The important thing here, the difference is that what I was interested is in measuring at what time in the Greenwich meridian, okay, the UTC time is called, okay, the Universal Time Coordinate, that is what UTC stands for. At what time UTC would the shadow in the place where I was would be the shortest? All right, and so I calculated at 728. So I did the calculations, so I called it at 7 hours, 28 minutes, 30 seconds, okay? So that was the shortest shadow at my location. So what happened is basically that noontime is 448 and a half minutes later than over the prime meridian. Okay, and we already talked about that in the other lesson. So this is the next try of that. And so I have 4 minutes is 1 degree. And so how many degrees would 448 and a half minutes be? Okay, and that gave me that you do the cross product, okay, and so it's 112 degrees, 7 minutes, 30 seconds. Okay, so that was my answer now. All right, so the next thing to do was to verify that. And so I went to Google Earth and put there my home. That is where I did the measurement. And my home is actually at 111 degrees, 54 minutes, 38 seconds. Okay. And so, and this other point here is at my result. So I measured that distance and I got an 11.17 miles error. much better than the previous time. Okay, you remember the previous time I had 110 miles of error between my measurement. Okay, so this time I was a little bit more patient, I guess, all right, trying to measure things more carefully, and I got a much better result, still 11 miles of error. Okay, so, good for Pablo, I guess. Okay, you can say, it's getting better, all right. At the same time that I was trying this experiment, I also basically tried to do the latitude experiment. Let's see, come on, guys. Okay, let's see, that is the next. So I did a latitude experiment with that, and so I measured the length of the shadow, okay, 10 and 1/8, okay, 10 inches and 1/8, and then I measured the length of my stick, my contraption, okay, and that was 5 3/4. Okay, so now these are pretty rough measures, all right, because I was using a pretty, big ruler, not something very precise. The more precise you are in your measurements, the better off you are. Okay, but in this case, I was doing that, all right, and so I did the calculations. Now these are the calculations for latitude. So my stick height, okay, 5 3/4, 5.75 inches. The shadow, 10 inches and 1/4, 125, 1/8, okay. And so I divide the opposite side, the shadow, by the length of the stick to find the tangent, and the tangent here is 1.76. Then I do the inverse tangent of that, and this gives me 60.4092526 degrees. Okay. Then remember that for latitude, I need now to correct for the solar declination. And remember that I was, let's see, I send you to this website, okay, of the National Oceanic and Atmospheric Administration, NOAA, all right, to look at the declination of the sun for the day where you were doing your observation. So I put my pointer there at my place where I'm doing the measurement. I changed the day to the date when I was doing the measurement, January 22nd, okay. And then I saw here the solar declination. That means this is how many degrees off the equator the sun is at that particular day. All right, and that is because again of the tilt of the Earth axis. So it's minus 19.61 degrees. And so we go back to there, and so the correction, I need to do 60.4 minus 19.61. That gives me 40.7995, and then I remember also how to translate these decimal degrees into degrees, minutes, and seconds. Okay, you subtract the degrees, you have that, then you multiply 7995 by 60, and that will give you 47 point something, and that is the minutes, and so on. Okay, so now we have my measurement here is 40 degrees, 47 minutes, 58 seconds. So how well did I do here? So again, my home is here, my measurement, the second try was over here, all right, close to, North Salt Lake. So I had a 31-mile error. So this was worse than my first try when I did this. The first try, remember here, okay, when I was doing there, My answer was 40 and 16, okay, and the real was there. So I had actually just a few miles going this way of error. Why was the difference? Well, in this experience, I had a much larger stick. Okay, and my stick was larger, the shadow was longer, so I have a more precise measurement there. Okay, in this case, I didn't have to correct for the declination of the sun, also because it was during the spring equinox. All right. In this case, I had to correct for the declination, and my measurement was a lot rougher, really. So if you have a more accurate measurement, you would have less error. But still, pretty good. So here you can see my measure of longitude and my measure of latitude. So if I would have just plotted these 2 points with my metric, I would have been around here in this area. Okay, so that is where I would have positioned myself instead of there. Okay, so that was my second try there at measuring latitude and longitude. Okay, I did a third try for latitude, and I used an inclinometer. I made a thingy myself. Okay, okay. This is all in the lesson thing, right? Okay, I will have to go over it again while it's in the midst. Yes, so you certainly have this material in the lesson, and I'm going to also post the video here in the lesson. All right, so you can rewatch the video, you can go forward and backward and so on. You can stop there at the screens where I do the calculations and whatnot. Okay, so you will have all the stuff there. So yeah, so kind of MacGyver type of thing. I got a PVC pipe, all right, a small PVC pipe, and I tape a protractor to the PVC pipe. This protractor had a little hole right there in the middle, and so I tied a string and I put a weight there at the bottom of the string. Okay, so voila, there I had my inclinometer. And so this is what I did at night to measure latitude. So this is kind of dark because it's at night. I also had to wait for a clear night, and so on in order to do this. I was trying to now measure latitude shooting the star Polaris. Okay, so let's see where we go with that.
Okay. Okay, so now we're going to remember to focus, okay? Mm-hmm. All right. Now we are going to shoot the star Polaris. Okay, and this is now easy. It's really a nice clear night. So I can see it right there. Okay, and now we have the angle. So we're going to see the angle there. Okay, and it's from 90, so 10, 20, 30, 40. 40 degrees. Exactly, okay, 40 and a little bit over. So 40 degrees, let's say 30 seconds. Okay, let's see how that goes. So that is how you measure with the inclinometer. Okay, you can stop.
All right, so did you see how it happens with the inclinometer, how you do it? So you have to remember, let's go back here to the inclinometer slide. You need to count from 90, okay, because that is where it would be, the angle would be if the thing would be horizontal, if the stick would be horizontal at the horizon, that would be 90 degrees. So you start counting from 90 to where the line falls, as you shoot Polaris right through the middle. It's not easy because Polaris is actually not a very bright star, okay? So I had to actually wait until it was dark enough. It had to be a clear night. I have the disadvantage that looking north from Saratoga Springs, you have all the lights of Salt Lake City, and that makes it even harder. But I was able to shoot it pretty good, and so when I had Polaris right there in the middle of my site, that is where I did the measurement, and it measured 40 degrees. Okay, so it was from here, it was 10, 20, 30, 40 degrees and a little bit, so 40 and a half, okay? So with that, you see that, what was it? So my real is 40-31, so very, very close, really, okay? All right. Yeah, so thank you. So yes, you need to count there from the middle, okay, from the 90 degrees. So if my position is 40 degrees 31, that was actually a very, very pretty accurate measurement, okay? So Polaris is actually much easier, all right, to shoot than the other ones, okay, doing the solar measurement, okay. Oh, no, cancel that. We are not going to end anything yet. Okay, so let's see. So that is how you do it. Do you have any questions, please? Now I show you different ways of measuring latitude with the sun and measuring latitude with Polaris. And I showed you how to measure longitude with the sun, okay, using the length of the shadows and doing all your calculations. And you need a clock and then some ingenuity, some MacGyver type of thing to do the rest, okay. Any questions? Okay. All right. So seeing there's no questions, okay, everyone either fall asleep or I don't know what happened, but anyways, I wanted to share with you something else that I found, okay, on my vacation. So let me go back here to the life here of John Harrison. There's, by the way, a movie that you can watch even online. I watched it online, and it's called Longitude, and it's produced by the BBC, I believe, on the life of John Harrison. It's pretty good. There's a couple of scenes that are not necessary, and they are not that bad, but they are really not highly recommended. Okay, but the movie is just amazing, really. And so here we have this article on John Harrison, the things that he did, and the clocks, especially, that he made. Okay, and as I was there on vacation, after we went to Disneyland, we went to Laguna Beach, and it's kind of an upscale area of Southern California. And I was walking around and everything, looking at the windows and everything, and I happened to see a jewelry store. And in this jewelry store, they had on exhibit a replica of the H1 clock. This is a replica of John Harrison's first clock that he did. Okay. And so I asked permission there to the store people if I could take a couple of movies of that. So let's see what we can see from here. This is a beautiful clock, very similar to John Harrison's H1. You can see it's fully encased, and it has the grasshopper mechanism here. You see how it releases one side and the other one, and they are in opposition, making the second hand stop, and the moving of the balances is what gives the motion to the clock. Beautiful, beautiful piece of machinery. Let's see if I can have a better angle here to show the back of the machine and the gears in there. Beautiful specimen. Very similar to H1 by John Harrison. And then I went inside and I asked if I could shoot a video from the inside, and this is the second one. So yeah, this is a replica of the H1 by John Harrison. You can see here on the back the legend there, and they are handmade in England, replicating the mechanism that John Harrison made for the H1. Needs winding once a week to wind the mechanism here inside, this part there, to give the energy for the balances to keep going. Has the grasshopper mechanism. All right. So what do you think? Yeah, so once a week you need to wind it. So he was British, he wasn't Swiss. All right, the Swiss, improved later on the chronometers. They became really experts in that, but John Harrison was really the one to invent and create a lot of these parts and things. Okay.
I bet he was referring to like Swiss as in Swiss Army knife, you know.
Well, the people in Switzerland are very famous actually for clockmaking nowadays.
Yeah,
okay.
I'm pretty sure he was referring to the knife. Like,
could awesome. Have been. Yeah. So, but yeah, he had to make all these pieces by hand. All right, they had to forge each single piece. Okay, they had to actually, create and modify the pieces and everything. This clock, the H1, Harrison took on a voyage. Okay. So yeah, so Sabrina says, no, it's the Swiss clocks and chocolate, not the knife. So it's interesting because the Swiss are famous for their clocks and chocolate, okay? And like we can see, John Harrison was a British. He invented the first chronometer. No, it wasn't the Swiss. And the chocolate doesn't come from Switzerland either. It comes here from Central America. So, but they certainly specialize in making things better, really. Isn't that interesting? Very, very interesting. This watch, the store people told me, they make just a few each year by hand, and is $15,000. Okay. And
have you? I was just thinking, I don't know if I've told anyone that I do have my own forge, and I get to go outside and I get to stick a piece of metal in there and I get to warm it up and pound it on the anvil.
All
and
right.
Look at something as complex and magnificent as this, and I can imagine just the craftsmanship needed to make those gears. I'm pretty sure they used files.
Yes.
For every those gear marks.
Oh, so anyone that has had a chance to work on a forge, and with metal and really molding metal, you can appreciate the craftsmanship of this piece. It's just amazing.
Because I could just see him trying to file the grooves, and he just goes over a little bit,
Oh,
and you have to roll the whole piece away.
yeah, that's right.
Start over.
Yeah, yeah. So anything, if it's out of balance, if it's not exactly perpendicular things, the whole thing has to be perfect, really.
Now, how did they get a round ball? File that thing?
I don't know really what it took to make these pieces of machinery, but it's just amazing, really. So here you have the H1 image, and this is now in the Maritime Museum close to Greenwich in London. And I kicked myself because I didn't go there when I was in London. I had a chance to go twice, and both times I couldn't make it to the Maritime Museum. So, see the progress really. Okay, so before this clock, before the H1, all the clocks had pendulums, all right? So they could only, swing if they were stationary. But imagine if you take that on a ship, what would happen to the pendulum? It would go all over the place.
Because it would go all over the place. It would lean from one side to the other. It rolled really fast. I mean,
that's right, yeah. And so this one, the H1, it was an amazing improvement because it was impervious to the movement of the boat. No matter how much the boat moved and everything, these balances kept moving at the same time, at the same pace. Okay, so if the boat moved this way or pitched this way, it wasn't a problem. What John Harrison discovered when he was testing the clock was that every time that the boat turned, okay, and it jawed this way, then the balances would, because of the centrifugal force of the, let me put the webcam here so I can record that. Okay, so if the boat moved this way or this way, it wasn't a problem with this clock. The problem was when the boat turned, the centrifugal force of the turning would make a very, very small, it was kind of, fractions of a second for each turn, and that the balances would be a little bit late. Okay, and so over time he would lose a few seconds per day. Okay, with the clock. And so that was why, after spending 5 years on this clock, he spent 3 more years on the next one, and then 17 more years until he got to this one. Okay, to the H4. All right, let's see if we can see that, to this one here. Okay, and this is completely different. It's all encased in this, and this one was completely safe from any movement. Okay, so very, very interesting story. So I really, really want to invite you to read this article on John Harrison, both the article that is in the family school, okay, this one here, all right. Read the lesson. It's not just interesting, it's fascinating, really. And really the persistence of the dedication of his life to doing this. And all of this so people could measure longitude safely at sea. Okay. And then, of course, read the article also here in Wikipedia on his life and everything, and you can keep going with that. All right. So I really think that is a fabulous love story. Mm-hmm. So, in fact, some of the first clocks that John Harrison made were made out of wood, okay? And then he also experimented on using different metals in order to prevent the clock from shifting with the heat expansion, changes in temperature. Mm-hmm. So, yeah. Anyways, any questions on this?
When was it invented or created?
Okay, so let's see here. This was in the 1700s, in the late 1700s. Okay.
Pocket watch, basically.
So let's see if we have the 1750s, the Jeffrey watch H4. All right. So about 1760s. Okay. So around that time. Finally in 1773, when he was 80 years old, Harrison received the monetary award in the amount of 8,750 pounds from Parliament for his achievement. So finally, after many years, it was a big battle actually between it was called the Board of Longitude and Harrison for this prize, because they didn't want to admit that he had won the prize. Mm-hmm. And finally, Parliament awarded him the money, but he lived only 2 years after that, and died. So his whole life was dedicated really to the measurement of longitude. Mm-hmm.
It almost seems like, from a few stories I've heard, that the Parliament was always kind of mean back then. They wouldn't give credit.
Well, part of the problem in the movie, okay, and in the book that tells about this story, what happened was that there were two camps, okay. In the Board of Longitude, there was one camp of people that thought that the answer to the measurement of longitude was with measuring time, okay, with the watchmakers. The other camp was the astronomers. And the astronomers kept thinking, no, we need to find a way of measuring longitude using the lunar distances and almanacs and so on. Okay. And for a long time, and I don't know if you remember when reading Carry On, Mr. Bowditch, that is what Mr. Bowditch used. He used lunars, to measure longitude, and he was very good. He improved the work of that tremendously, but it was still very cumbersome, really. And so it wasn't really until the clocks of Harrison were available and became cheaper to make, and they started to make them more en masse for all the ships. Before that, everyone had to use this astronomic type of measurement. And so there were these two camps of people kind of fighting between the horologists, okay, the people measuring time, and the astronomers, okay. And so the board was kind of more on the astronomers' side, and so that is why they didn't want to give the prize to Harrison. But Harrison, just it was just amazing, the accuracy of his clocks. Okay. And then Captain James Cook used the K1, that was a copy of H1, in his second voyage, and he came back and gave a report, all right, about that. And so that is kind of what convinced everyone, yeah, this is worth investing in. Okay. Yeah. There's a lot of writing in his tombstone, I guess. Yes. Let's see. Yeah. So there it tells probably a lot of his life story. Okay. And then also he has this is where he lived, okay, in London. And then this is a marker in Westminster Abbey, where you have all the kings and queens of England and a lot of famous people that are buried there. John Harrison is not buried there, but he has a marker there, and you can see here measuring the longitude in this piece, 0 degrees, 7 minutes, 35 seconds west. Okay, so that is where Westminster is from Greenwich. Very, very interesting story. Okay, so what lesson do you learn here from the life of Harrison? Yeah. Yeah, James Cook was a very famous British captain. He discovered the Hawaiian Islands, among several other things. What lesson do you learn from the life of Harrison? What gospel principle do you think you can apply to your life?
I'm thinking, really trying to learn here. In the creation of that clock, could have had to mess up many times, but he didn't. What I can get from that is, no matter if I set myself up to accomplish something, I should not give up until it's done.
That's right. Yeah. Perseverance. Okay. Never to give up, even if it takes us our whole life. Okay. To keep going. Repentance, Sabrina points out. Change. It is very interesting because when Harrison created the first clock, and it was very, very accurate, no one knew that it had a flaw. No one knew about this error. Remember when I was mentioning that the error that when the ships turn, no one noticed that. He knew. Okay. And so that wasn't enough for him. He wanted something that was more reliable, and that's why he spent, many, many more years improving and coming up with new mechanisms and new things. Okay, praying a lot probably to get inspiration on how to do this. Ashlyn says redemption. The perseverance, the finding and improving on faults and so on also brings redemption. He chose something to make and to create, something unique. So a lot of you have mentioned to me, and to the class that you like writing, you like singing or playing music, all right? So whatever it is that you choose to do in your life, just remember the integrity, the perseverance that it takes, okay, in order to keep moving forward. He certainly used his talents for good. The thing that moved him the most was knowing that measuring this longitude correctly was actually saving lives. Anik Abigail says he obviously had a lot of integrity because he could have just left it error and move on with his life, but he wanted perfection. That's right. Yes, he wanted to do something completely right. Hmm. It's a lot of
He
hard
wanted
work.
something
Hmm.
right instead of money.
Yes.
I said, yeah,
Hmm.
wanted something right more than money, which
Yeah.
I've been hearing stories that nowadays people make products that are less reliable but are the same price.
Hmm.
The other day I heard a story that they're now making ink cartridges with less ink in them for the same price.
Yeah. Hmm.
Yeah.
There's
They
no
just want,
integrity, so a lot of people fall for, doing the cheap thing, the easy thing, the fast money thing. Okay. So I really want to point out, that is not what we should do with our lives. Okay. All right. Well, thank you very, very much. I just couldn't pass sharing this lesson with you guys. Okay, because when I saw it, I knew that I was out of town last week and everything, but I was like, hey, this is fabulous material, and what a great, great example, and really a true love story for me. To think about this. So many things that we can learn here. Okay. So again, I want to encourage you to try the experiment, try to do the measurement of latitude and longitude, review the materials in this lesson, how I did it. Okay, as you can tell, I use very, very cheap things, nothing very difficult. Okay, and give it a try, and you will have some errors. Okay, and that is fine. The idea is to keep trying and getting better at it. Okay, that is how science is. All right. So, who would like to offer the closing prayer today? Do we have someone with a mic? Nicola, do you have a mic available?
If you can hear me.
Yes. Yeah. That is
Okay, give me just a minute.
Yeah.
Our dear Heavenly Father, thank thee for this day. Thank thee for Mr. Boldy and the great lesson he gave today. Thank thee for all of us being able to gather as a class. Please help us all to have a safe evening and rest of the day. And I say these things in the name of Jesus Christ, amen.
Amen. Thank you very, very much to everyone. Okay, and we'll see you next week.